All right, let's get right into it. Think about every single digital device you own, your phone, your laptop, even your gaming console. Deep inside each one, there's a brain. It's the central processing unit, the CPU, and it is the absolute engineering marvel that runs our entire digital world. And in this explainer, we're going to pull back the curtain on its most fundamental secret. So to really get a sense of where we are today, you have to see just how far we've come. On the left, that's the heart of a 1983 Apple IIe. It had just over 4,500 transistors and could pull off maybe 500,000 calculations a second. Now look at the right, a modern M1 chip. We're talking 16 billion transistors, and it can perform around 3 trillion calculations every single second. Yeah, the leap is just mind-boggling. But here is the really wild part. Despite that insane gap in power, these two chips, and honestly pretty much every processor ever made, share a common piece of technological DNA. It's this one fundamental principle that makes everything work, from the simplest games of the 80s to the most complex AI of today. So what is this shared secret? To get our heads around this, let's use a simple analogy. Forget all the transistors and circuits for a minute. Instead, I want you to picture a lone robot, working all by itself in a giant library. Believe it or not, this simple scene holds the key to how every single CPU actually thinks. First up, imagine these endless rows of bookshelves. This is your computer's main storage, its solid-state drive, or SSD. This is where everything lives long-term. All your programs, your files, your photos, they're all just sitting here like books on a shelf, waiting to be picked up.
Now, our robot can't work directly from those giant shelves. It's just not efficient. So it uses a little cart to bring a few books over to its workspace. This cart? That's your DRAM, or what you probably know as RAM. It's the temporary, super fast memory that holds only what you're actively working on right now.
And that workspace, the robot's table, that's the CPU itself. This is the main event. It's the central hub where all the action happens, where instructions from the books are actually read and all the real thinking gets done.
On that table, there's a small sheet of paper. Think of this as the CPU's registers. It's a tiny, ridiculously fast little scratch pad for jotting down the exact numbers and values the robot is working with in that very instant. And finally, the most important tool on the table, a simple calculator. This is the ALU, the Arithmetic Logic Unit. This little guy is the mathematical core of the whole operation. It's the part that does all the basic math, adding, subtracting, and comparing numbers.
Okay. So we've got our robot, our library, our table, and our tools. How does it all come together? Well, it all comes down to a simple, endlessly repeating 3-step dance. This cycle is that technological DNA we've been looking for. It's called fetch, decode, and execute.
And it really is this simple. First, the robot fetches the very next instruction from its book. Then, it decodes it, basically figuring out what on earth it's supposed to do. And finally, it executes that command using its tools like the calculator. Fetch, decode, execute, over and over and over. This simple loop, repeating billions of times a second, is literally the heartbeat of all computation.
Let's break that down just a little bit more. So for the fetch step, how does the robot know which instruction to grab next? Well, it keeps a special number on its little scratch pad called the program counter. This number is like a bookmark. It always points to the exact location of the very next instruction it needs to perform. Next up is decode. See, the instruction the robot fetches is just a string of ones and zeros. It's binary. So that code gets fed into a special circuit, kind of like part of our robot's brain, that acts as a translator. It looks at the binary pattern and figures out, oh, okay, this means add these two numbers, or this means store this value over here. And that brings us to execute. Once the command is understood, the CPU just does it. Electrical signals fly, maybe some values get moved from the registers, our scratch pad, over to the ALU, our calculator, to get crunched. The work actually gets done. And then, as soon as it's finished, the cycle starts all over again with the next instruction. Billions of times, every single second. So here's the kicker. This whole cycle works with a list of really simple instructions. You might be thinking that a modern computer must need, I don't know, tens of thousands of different commands to do all the amazing stuff it does, but you would be really surprised. Let's go back to that 1983 Apple IIe. Its entire vocabulary, the total number of unique commands its little brain could understand, was just 56. That's it. With a language of only 56 words, it ran games, word processors, and an entire operating system. Okay, so what about a brand new M1 chip? Its vocabulary is bigger, for sure. It has 354 unique instructions. But think about it. That's more, but it's not a million times more. And that tells us something really important. The secret to all this modern computing power isn't just about having a giant dictionary of commands.
And this really says it all. It doesn't matter if you're watching a movie, playing the latest AAA game, or running a complex scientific simulation. Every single thing you do on a computer is just built from different sequences of these basic, simple instructions, just executed at a completely blinding speed.
So if that fundamental cycle is basically the same, and the number of instructions hasn't exploded, then how in the world did we get this incredible increase in power? Well, the answer isn't in changing the process, but in supercharging every single part of it.
Just look at the raw numbers here. The old 6502 chip had a clock speed of 1 megahertz. That means its fetch, decode, execute cycle could run 1,000,000 times per second, which is fast, but the M1 runs at 3.2 gigahertz. That's 3.2 billion cycles per second. On top of that, it can chew on 64 bits of data at a time, where the old chip could only handle 8. So it's doing way more, thousands of times faster. But it's not just about raw speed. Modern processors have all these brilliant engineering tricks. Take pipelining. It's like an assembly line. The CPU starts fetching the next instruction before it's even done executing the current one. Then you have huge caches, which is just like giving our robot a much bigger table to work on, so it hardly ever has to go back to the cart for more books. Multiple cores is easy. That's literally like putting several robots and tables in the library, all working in parallel. And then there's branch prediction, this incredibly clever trick where the processor literally guesses what you're going to do next just to keep that assembly line moving at full tilt. So there you have it. For over 50 years, this simple cycle, fetch, decode, execute, has been the technological DNA at the very heart of our world. It's been tweaked, optimized, and accelerated in ways that feel like straight-up magic. But it does leave us with one final, huge question. What comes next? If this was the DNA of the first 50 years, what's the fundamental DNA of computing going to look like for the next 50?